Okay, everybody can see those again. Great. And now I'm seeing no one, so that's good. All right, yeah, like I said, we're going to talk about three different t-tests tonight. One sample, two sample or independent t-tests, and then the dependent or what's also called paired or pairwise t-tests, multiple names for these. And again, all of these, each of these three, you can do them rather easily in Vassar Stats. But as you know, there's lots of other software packages out there, browsers that you can use. Calculator Soup might be a good one if you just simply Google, like independent T formula or one sample T formula or something like that. Calculator Soup likely has something like that. And the nice thing about programs like Calculator Soup, if you noticed Vassar Stats wants you to enter numbers separated by returns, and they don't want you to have like an extra return at the bottom. Otherwise, it thinks you have an extra term. Whereas Calculator Soup, it just does like a free-form thing. It can be separated by tabs, spaces, commas, returns, a lot more flexible when you enter your data. And one of the things that might help with is if you're on a quiz in Canvas and you're able somehow to copy and paste data from your quiz and put it into one of these browser windows, then that might be quicker. So anyway, again, I'll show you Vassar Stats, and I'll leave it to you and your teammates to think about going over and using other stat package things like that. And again, I strongly encourage you. We got lecture tonight. If you're not doing anything tomorrow night, maybe set up a Teams meeting with your team and go over some of these things. And then even, Thursday before the test at 6:30, you could meet like at 5 or 4 or something like that and go over things. Again, that's always up to you. Okay, so let's start off here. And this is again an introduction to inferential statistics. So we'll take a little bit extra time tonight because I want you to understand what inferential statistics really means. Now, so far, in a whole 1 week, we've talked about descriptive statistics, which is things like mean, median, mode, standard deviation, range, things like that. Descriptive statistics are tools that we have to help us with large data sets, large sets of numbers. And the sole purpose of those is to help us describe that data set. If someone takes a test, let's say that your loved one, parent, child, brother, sister, whatever, is taking a chemistry test in college, and they come back and they say, "Yeah, I took the test and I got a 59 on there." Well, the 59 itself doesn't really tell you much. Is that 59%? If so, that means you got, less than 6 out of 10 right on average. Is it 59 out of 60 total points? That's pretty impressive. Is it 59 out of 200 total points? That's really not good. So we use descriptive statistics to help us to better understand what the data mean. So, the mean there could help a lot. If I got a 59 on a chemistry test and the mean was 47, that's pretty good. I scored quite a bit above average. And, if it's a skewed distribution, you might want to know the median rather than the mean. What's the most common score? And then you might want to know how spread out those scores are. If the mean was 47, does that mean that everybody was sort of bunched right around the mean? Or does it mean that it was pretty much evenly scattered all the way through? So tonight we're going to take a turn and instead talk about inferential statistics, which is where we take a sample. And you know what a sample is? A sample is you collect data from a population, and we take that sample and we want to use that to infer about the population. Now, we've talked about sample statistics like a mean, median, standard deviation, but there are also population parameters. And that's like, the real thing out there in the population. So, the population parameter for SAT average is everybody who took the SAT verbal in 2025. This is the actual mean of the set of scores, and that could be millions. But like I said, we rarely have access to population data. So instead, we usually take samples and we try to get the best, most representative samples we can, and then compute sample statistics and infer what the population parameters might be. So inferential statistics is what we're going to talk about for the next 4 weeks, all types of different tests, ANOVA, correlation, things like that. Those are all examples of inferential statistics. And each one of those will be having a problem where you have a sample and we're trying to take that sample and draw inferences about what the population parameters might be. Okay, so that's the first step. So now let's look at this problem. So, and forgive me, I'm always using examples for like health, like smoking, cholesterol, things like that, because that's what old guys like me are into these days. We try to find ways to stay alive. So cholesterol is a fatty substance that forms deposits on the inside walls of arteries and is believed to contribute to heart attacks. Assume that the mean cholesterol level in the blood of a population consisting of men in the 55 to 65 age group, I'm in that, is 170 milligrams per 100 milliliters of blood plasma. Suppose you draw a random sample of 37 men in that age range who have suffered heart attacks and measure their cholesterol levels, obtaining the data given below. Are the cholesterol levels of these men higher than the population? Okay, so I've got 37 scores there that represent 37 men randomly sampled, and I'm measuring their cholesterol. And most of you are familiar with cholesterol levels, right? For the most part, we want cholesterol levels below 200. Anything above 200 starts looking kind of scary. So we're trying to lower our cholesterol. So you know what these numbers mean. And we know that the average cholesterol level for that particular age group of men is 170. So we want to take now a sample of men in that same age range, but these men differ from the normal population in the sense that these are men that have suffered heart attacks. The other men out there in the population, they don't necessarily have had a heart attack. They're just everybody else in the population. So we want to know here, do men who have had heart attacks, do they typically have higher cholesterol than the general population? Seems like a good question, right? And in this sense, I would bet most of you, if you had $10 to bet, and you didn't even look at the scores beforehand, you might say something like, well, yeah, it's very likely that the men who have had heart attacks are probably going to have higher cholesterol levels than the general population. So since you have a strong hunch like that, that's where we start talking about one-tailed and two-tailed tests. If we are confident that the cholesterol levels of men who have had heart attacks will be greater than the general population and very unlikely to be lower than, then we can conduct what's called a one-tailed test, where we put all of our marbles, so to speak, that we're betting on one side, and we say, hey, if there's going to be a difference, it's going to be that the heart attack men are going to have a higher average than the general population men. And so I'll explain more about one-tailed versus two-tailed here in a bit, but that's why you would conduct a one-tailed as opposed to a two-tailed test. Okay, so this is the one sample t-test. I know I should have had these appear kind of one bullet at a time. Sorry about that. I'll have to go back and fix that. So here's our research question. We wish to know if the population mean cholesterol level of men 55 to 65 who have had a heart attack is greater than the population mean, which is 170, of men in the general population of that age. We know one population mean, but we don't know the other one. We know that the population mean for all men in the age range is 170, but we don't know specifically what the population mean is for men who have had heart attacks. To estimate, to infer what that population mean is, we gather a sample, and we have 37 men in that age range who have had a heart attack. We're going to then compute statistics on that sample, and then we're going to compare those with the population mean. And then is the most difficult part of understanding inferential statistics. We don't just compare them and say, oh, it's higher or it's lower. We have to know if there's a statistically significant difference. And the concept of statistical significance is a tough one. See, a lot of people don't understand that. And there's a lot of professors at universities that don't know what that means. And I don't mean that arrogantly, and I don't mean that in a condescending way for them, but that's just, it's a real tough concept to understand. So hang in there with me tonight. I want you to see if you can understand that. So yeah, we're going to collect a sample, use that to estimate the population, then we compare that to the known population. All right. So whenever we do a statistical test, we have what's called a null hypothesis. And you should have read about null hypotheses and know a little bit about what those are. So a null hypothesis is never a question. It's always a statement. And the statement has to be something that can be true or false. It can't just be like, hey, the statement is most people are happy or few people will get bitten by snakes. No, a hypothesis is a statement something like, the population mean cholesterol level for men who have had heart attacks is the same as the population mean for all men. You're thinking like, well, why would you say that? We know it's not going to be the same. Well, that's why it's called a null hypothesis. Null means zero. And if you see on the far left side here, this capital H, that's hypothesis. And that's not a little o, that is actually a subscript 0. Subscript kind of, borders the bottom line. So that's H sub 0, or the null hypothesis. The population mean cholesterol level for men who have had heart attacks is the same as the population mean for all men. We can express that a few different ways numerically. Now, to truly make it a null hypothesis, we can state the one just below that. And these are mu. Remember, mu is a Greek symbol, lowercase mu, stands for a population mean. So when we talk about ANOVAs and t-tests, we're going to use these mu's a lot because those stand for the population mean of particular groups. Now we have subscript G here for this mu, and that means the mu or average cholesterol level for the general population of men 55 to 65. This mu sub H is for the same age group, but men who have had heart attacks. And if I subtract one from the other, I get 0. A null hypothesis always has to have a 0 value, right? So that's the true null hypothesis. But another way of saying this, which means the same, is that the population mean cholesterol level for men who have had heart attacks is 170. Why is it 170? Because 170 is the general population. And we know that we're saying up here, it's the same. So it could be, mu H equals mu G, or mu G minus mu H equals 0, or we know one value, so we'll just say mu H equals 170, which is the same as mu G. And that's our null hypothesis. Sorry, trying to go back here. Okay. Yeah, that's our null hypothesis. Okay. So again, if you have a question, just unmute yourself because I can see no one from this small laptop. So we always have another hypothesis, and that's called the alternative hypothesis. Now, the alternative hypothesis has to be mutually exclusive of the null hypothesis, which means that there's no conditions that would satisfy both, where both could be true. You either have one true or the other one true. They both can't be true. So the alternative hypothesis is a statement of a non-zero difference or relationship concerning an unknown parameter. We know what our unknown parameter is here. It's the population mean cholesterol level for men who have had heart attacks. So this H sub 1 here, and sometimes you also see H sub A, capital A, that means alternative hypothesis. This H sub 1 just means this is our first alternative hypothesis. Sometimes statistical tests, you can have multiple alternative hypotheses because you're testing multiple research questions and things like that. All right, so our alternative hypothesis simply says the population mean cholesterol level for men who've had heart attacks is greater than the population mean for all men. that's based on our hunch earlier that like, yeah, normally people have heart attacks, they have higher cholesterol. That's pretty common sense. So if we are very confident that we think it's going to be greater, then we can use this greater than sign in our alternative hypothesis statement and say the mean cholesterol level for heart attack guys is higher than the non-heart attack guys or general population. All right. And again, these null and alternative hypotheses will become clearer later, but this determines, what your sampling distribution is going to be that you're using and all kinds of things. So one of the things that we calculate with inferential statistics is something called degrees of freedom. And remember, we had that n-1 in the denominator for sample variance and sample standard deviation, and we didn't have n-1 in the denominator for population. Well, we're always using samples. We're never computing populations, right? So we're going to be using n-1 a lot as we compute inferential statistics. So in this particular case of a t-test, the n-1 is going to be degrees of freedom, and that's the number in the sample minus 1. So we have 37 scores, 37 cholesterol levels of the men with heart attacks. If we subtract from that 1, we get 36, and that's our degrees of freedom. We're like, what is degrees of freedom? What does that mean? Well, because standard deviation and mean are conducted with parametric statistics, and because they're precise measurements, you can divide, you can multiply, and things like that. We have to know how many scores in a sample are free to vary for this particular test. And what does that mean, free to vary? Well, they can actually be anything they want. But once we have an established standard deviation, let's say our standard deviation is 2.4 and our mean is 8, then 36 of the 37 scores can be whatever they want. They're free to vary. But the very last score has to be a specific value in order for us to get a standard deviation of 2.4 and a mean of 8, just as an example. So that's what degrees of freedom mean, is that once you've calculated like certain statistics, all of those scores can be free to vary except one, because then it has a particular set value. Now, again, not many faculty members can tell you what degrees of freedom are. If you want to ask one of your professors or instructors over the next semester or two, you can really get under their skin and make them angry because you'll embarrass them. Or you could just choose to believe me and say most don't know that. All right.
So are we ever going to have to calculate degrees of freedom? Like to determine the number ourselves?
Yeah. And Brian, the formula will be as complex as something like n-1.
Okay.
So there really is no difficult calculations for degrees of freedom. It's mainly knowing what the formula is, and then it's like, oh, I subtract that and I get this. So
okay.
Yeah.
Got it.
Yeah, good question. Okay, so we've got this one sample t-test, and we're calling it a one sample t-test because in this problem we have one sample. We have a sample of 37 men who've had heart attacks, and we have their cholesterol levels. We have 37 scores. So we're going to be comparing that one sample to a population parameter, right? So we're going to compute a mean from that sample, and we're going to compare that to the population parameter, which is 170. Now we've got to talk about these things like type 1 error, type 2 error, alpha, things like that. And this should help you understand that terrible question that said, what happens to the critical region? I'll just tell you up front, the critical region is determined by alpha. And if alpha is 0.01, that means that the size of your critical region is 0.01. That's 1% of the area beneath the normal curve. And if you set an alpha of 0.05 or 0.10, the critical region then is 0.05, 5%, or 10%, something like that. If you have a two-tailed test as opposed to one-tailed, and alpha is 0.05, then you have 2.5% over here in this tail and you have 2.5% in this tail because it's symmetrical. And if you have a one-tailed test, you have 5% of the critical region just in one tail, because the only way you can reject the null is for your sample mean to be greater than your population mean, like what we're doing in this problem. Okay, so again, some of this stuff will begin to get more clearer as we keep talking. I don't expect you to know what we mean by degrees of freedom and alpha at this particular juncture. But we do set alpha a priori, which means before we start collecting data, before we have hypotheses, we decide up front what alpha we want to use. And I'll just, spoiler alert, most people use an alpha 0.05. And I actually wrote a paper on that 30 years ago, why we use alpha 0.05. And you can reach it on my website. It's a really cool paper, but didn't get many people to read it. Anyway, okay. So when we do a statistical test, when we do an inferential statistical test, we're either going to find statistical significance or not find statistical significance. If we find statistical significance, then we are going to reject the null hypothesis. And you can see down here, our statistical conclusion, we're either going to do one of two things. It's called a binary decision. We either do not reject the null hypothesis, or we reject the null hypothesis. Those are the two decisions that we will make. And, if the null hypothesis is true and we do not reject it, then we've made a correct conclusion. Okay. If we decide to reject the null hypothesis, and in fact, the alternative hypothesis is true, then we've also made a correct conclusion because the null hypothesis is false if this one is true. Now, we can also make errors, though. Let's say that we decide to reject the null and say, yes, there is a statistically significant difference. Men who've had heart attacks have higher cholesterol than the general population, but in reality, they don't. Then we've made an error, and that one's called a type 1 error, also known as a false positive. A false positive means that you think you found something, but you really didn't. Okay. If my conclusion is to not reject the null, but in fact, the alternative hypothesis is true and I should have rejected, then I've made what's called a type 2 error. In other words, I didn't find a difference when I should have, or I didn't find something when I should have. That's called a type 2 error or a false negative. I concluded negative, there's nothing there, when in fact I should have found something. Okay. So if someone screens you for cancer, AIDS, coronavirus, something like that, and the test comes back negative, you're like, cool, I don't have that. But we end up finding out like a day later, like, yep, you really are sick, you have that virus or whatever. Then that was a bad test and they made an error. They made a false negative. On the other hand, if someone says, gosh, I'm sorry, our test has turned up positive for a very deadly form of cancer, we can expect to see you gone in about a month. And then you're thinking like, well, maybe I should get a second opinion because, this is my life. And you go get a second opinion, they run another test and like, yeah, there's nothing wrong with you. Well, they made a type 1 error. They made a false positive. So, all right, let me give you another example here. This one's supposed to be funny. Hopefully it won't be offensive anyway. All right, the one on the left, this is a type 1 error called a false positive. This doctor is saying, hey, you're pregnant. Now, looking at this person, that's not the typical person you see that gets pregnant. So that's definitely going to be an error there, saying you're pregnant when in fact he's not. He's had a type 1 error, a false positive saying, I think there's something going on here, but there's not. A type 2 error is when you fail to detect a difference or relationship or something going on, when in fact there is something going on. So this woman appears that she's pregnant, and the doctor is saying, hey, I don't think you're pregnant. She's making an error, and that's a type 2 error. So hopefully those funny comics are a powerful way for you to understand. Okay, So why alpha 0.05? Why do we use an alpha 0.05? So I want you to bear with me here, and I'm going to give you an example of why we use 0.05. So let's suppose that we're all in the same classroom and not online today. And I tell you that I've got a way to flip a coin so that it either comes up heads or tails, however I want, every time. And I throw it up in the air and it rotates at least 10 times. And every time it hits the floor and bounces around, I can call it and it comes up exactly how I want to flip it. Right. So most of you would be thinking like, well, that's probably not true. You should be skeptical, right? And let's say I have a volunteer and I say, okay, come up, let's make sure that, I'm not pulling anything. Have I talked to you beforehand? No. Are you in on this with me? No. Okay, great. You're going to be a good witness up here. I want you to witness all these coin flips. And let's say I'm even more fair and I say, does anybody have a quarter in their pocket? And someone raised their hand, gives me the quarter. I say, hey, have I talked to you beforehand? Is this a trick quarter or anything? Nope, nope. We're all in the up and up, right? And then I get the coin and I say, okay, I'm going to flip this coin. I'm going to flip it way up in the air, and it's going to land on the floor, but it's going to come up heads. And so I call my shot and I flip the coin. It goes way up in the air, bounces a few times, lands, and lo and behold, it comes up heads. Most of you would be thinking like, wow, that's pretty cool. But how many of you would be convinced at that point that like, wow, Dan can call his shot every time? That's really cool. No, most of you would probably say, I need to see a little bit more than that before I'm going to be a believer, right? And honestly, this is all about significance testing here, null hypothesis significance testing. It's whether you're a believer or not, because once you believe that something is going on, then that's called a significant difference or significant relationship. If you never do reach that point, you say, Dan flipped that coin once and it came up heads, but that's not that rare. I mean, lots of people could have no skill whatsoever. They flip a coin, there's a 50-50 chance it's going to come up heads. So, I'm not a believer yet. So then I tell you, okay, I get it. Let me do it a second time. So I flip it a second time, bounces around. I have somebody up there witnessing it, and they say, wow, it came up heads again. Somebody else want to come up and look? Yep, it's heads again. Not a trick quarter, nothing like that. I don't have a Confederate standing next to me who's saying it's heads when in fact the tail is showing. I've got two in a row. Well, according to the bottom there, two in a row, there's a 25% chance that whenever you flip a coin two times, that you're going to get two heads. There's also a 25% chance you're going to get two tails. And there's a 25% chance you're going to get a tail and a head in that order, or a head and a tail in that order. There's 4 possible outcomes when you flip a coin twice. There's one when you flip it once, and when you flip it 3 times, there's 8 possible outcomes. Okay. Let's say I flip it a third time. How many of you at that point are saying, I'm in, I'm all in, I'm convinced Robinson has magical powers or a certain type of skill where he can call his shot and he flips that coin, it comes up that way every time? Well, if you reached your breaking point at 3, then that's about a 12.5% chance of that happening due to chance alone, just randomness. And you might say, that's too rare. That shouldn't be happening by chance alone. So we did this experiment with people and gave them scenarios like this. And we found that most people's breaking point was somewhere between 4 and 5 coin flips. And look at the probability of obtaining those results, assuming the null hypothesis is true. Now, with coin flipping, the null hypothesis is that it's completely random, that however a coin flip comes up, it's due to chance, right? And when you see a coin flip at a football game at the beginning, that thing should be chance. That official should be flipping that up in the air a number of times so that there's no, bias whatsoever, and it should be completely fair. Most people, when we gave them a number of scenarios, their breaking point was somewhere around 4 or 5 coin flips in a row. And notice where the 0.05 alpha would be, somewhere around that point. Now, that also has a name for it. That is called the threshold of dismissing results as due to chance. And that's really what we're doing with significance testing, is we're reaching a point where we're saying chance alone, randomness alone can no longer explain these results. There's something going on here. And in this particular case, it would have to be the Confederate lied and they're just saying, it's heads every time when in fact it's coming up tails and heads. Or that person gave me a particular coin that's weighted and it always comes up heads or something like that. But when you suspect that fishiness, that there's something else going on besides just fair coin flipping, random chance, then we've got a statistically significant difference. And statistical significance just means this is a rare occurrence, assuming that chance alone would explain these outcomes. And if you're understanding that at all right now, then you understand a lot more about significance testing than other people do. Okay, so why is alpha 0.05? Yeah, that's why. Most people's threshold for the dismissal of results is due to chance is around 0.05. And here's an example of a two-tailed test. If we have alpha at 0.05, then we look at the area under that normal curve at a certain point, and 2.5% would be in the upper tail, 2.5% would be in the bottom tail, and there's 95% of the area of the normal curve in the middle. That's how we conduct significance tests. All right, let me keep moving here. Get a drink. In our example here, with the cholesterol, we used a one-tailed test, and we're saying the only way in which those are going to differ is that the men with heart attacks are going to have higher cholesterol. Then we would expect the sample mean to be above the population mean. And if it's up here in this critical region, we're going to say men with heart attacks have significantly higher cholesterol levels than the general population. If it's anywhere over in this region, we're going to fail to reject, and we're going to conclude that men with heart attacks do not have levels that are significantly greater than the general population, and we fail to reject the null hypothesis. Okay, so here's our formula for our t-test, our one sample t-test. We've got T over here, and T is our statistical test, and it's also going to be a value that we come at. T is an actual statistic because we're computing it based on a sample, okay? And in the numerator here, we have X bar, which means the sample mean. What's the only sample mean we can have? Well, we would compute a mean based on those 37 scores. And we subtract from that the population mean, which is 170. That's the mean cholesterol level of the general population. So this 195.41 is the average score of all those 37 that I showed you earlier. We we divide that by the standard error of the mean. Now, you guys are a little bit familiar with standard error of the mean from last time, but if you recall, standard error of the mean is the sample standard deviation divided by the square root of n. And if I do this, I get 25.41 divided by 5.41, and I get a t-value of 4.69. Now that t-value, because it's positive, tells me that the sample mean was greater than the population mean. Thus, I'm going to locate that t-statistic on the right side of my sampling distribution. It's going to be up towards the, the greater side, because we as an alternative hypothesis, we predicted that the sample mean will be greater than the population mean. And then we compare the p-value that we will get to 0.05. If that p-value is less than 0.05, then we're going to reject the null hypothesis. And that p-value, by the way, is a probability value. That tells you the probability of obtaining results this extreme or higher assuming the null hypothesis is true. You can go back and watch this recording later, but let me repeat that again. That p-value tells you the probability of obtaining results as extreme as this or greater, assuming that the null hypothesis is true. The null hypothesis assumes that there's no difference. So assuming that's true, if we calculate a statistic this large or this small, then we make a decision on like how likely would that have been attained due to chance alone, assuming that the null hypothesis is true. Well, if it's way out there, then it's less likely. It's kind of like 5 coin flips in a row. That's not very likely. That's pretty rare. So we conclude that because that's so rare, we think there's something else going on besides chance, and there's a real difference here. That's it. In a nutshell, that's hypothesis testing. So our conclusion here, and by the way, I'll go back and show you how to do these using Vassar stats. Our conclusion would be men aged 55 to 65 who recently had a heart attack have higher cholesterol than the general population of men who are 55 to 65. That's because our p-value that we're going to calculate there is going to be less than 0.05. If that p-value was greater than 0.05, and by the way, that's all you have to look at in Vassar stats, that p-value. If it was greater than 0.05, then our conclusion is there's really no difference in the cholesterol levels of men who have had a heart attack versus the general population. That's what we would conclude. All right. We've got 2 more t-tests to cover, and then I'll go back and I'll show you how to do all these using Vassar stats. Here's a different one. A pharmaceutical company has developed a nasal spray that supposedly reduces cholesterol. Again, with the cholesterol, right? They conduct a clinical trial where a control group receives nothing and the experimental group uses the spray once per day for 6 weeks. The cholesterol levels after the experiment are below. So now I've got 2 samples. This is also called a 2-sample t-test or an independent samples t-test. I've got a control group and I've got an experimental group. Right? Most good experiments, I have a control that receives nothing, and I've got an experimental group that receives the treatment. Okay? The treatment here is using the spray once a day for 6 weeks. The control group does nothing. After the 6 weeks, I measure the cholesterol levels of the people who had been using the nasal spray versus those who haven't. Okay? Now, in this particular case, I've got 2 samples. I don't have a population mean given to me up front that says something like, hey, the normal cholesterol level in the population is 170. Then all I would have to do is compare my experimental group to that. I don't have that. So to estimate what the population mean is for people who don't receive the spray, I have to have a sample of people who don't use the spray, and I'm going to use that to estimate the population. Just like I'm going to calculate a mean of the experimental group here to estimate what's the population mean of people who use the spray in terms of cholesterol levels. And by the way, this is one of the most common statistical tests. It's called a t-test. 2 groups. All you're doing is seeing like which one's higher or lower, things like that. So we want to know if the nasal spray reduces cholesterol. That's our research question. We don't know either population mean, the experiment or control, but we assume they are the same. Every independent samples t-test has the same null hypothesis. It is that the 2 population means are the same. Experimental control, male, female, whatever our groups are. So we're going to collect 2 samples, use them to estimate the difference between the 2 population means, then we compare that to 0. So here's the null hypothesis for an independent samples t-test. And by the way, this is the same null hypothesis for every independent samples t-test. It's going to be one population mean is the same as the other population mean. In our problem, it's men who use the nasal spray versus those who did not. Experimental versus control. You see the null hypothesis here. I've got my subscripts. This is mu sub s for the nasal spray group and mu sub C for the control group that didn't use it. I'm saying those two population means are the same. That if you subtract one from the other, you get 0. My alternative hypothesis is going to be that that difference is not 0. And if I want to use a two-tailed test here, I just say does not equal. That means that the nasal spray could have higher cholesterol or lower cholesterol than the control group, and I still have a chance to find a significant difference. When I have a does not equal 0 sign there for my alternative hypothesis, that means I'm going to have two critical regions, one for higher, one for lower. That means that if that cholesterol level went way down for men who use the spray, I should be able to reject the null. On the other hand, if for some reason that nasal spray caused cholesterol levels to go up, I can also reject the null hypothesis. I can find a difference in either direction. I'll use an alpha 0.05 because that's most people's breaking point. And Brian, here's a complicated formula for degrees of freedom. For a two-sample t-test, it's always this, n1 plus n2 minus 2. Another way of saying that is that's the number in the first sample minus 1 plus the number in the second sample minus 1. Or you can just add the two samples together and subtract 2 from it. That's the same thing, however we want to do it. I had 20 scores in my control group, 17 scores in my experimental group. That's 37. Subtract 2 from that. I've got 35 degrees of freedom.
Does the number 2 correlate to the number of groups that you have? So if there were 3 groups, N1 plus N2 plus N3 minus 3?
Yeah, but I can never have that with a t-test because the t-test is limited. It only works with 2 groups.
Okay.
Now, if we have 3 groups, we'll do what's called analysis of variance, which we will cover in the next few weeks. But for this one, this only works with 2 groups. Good question. Okay, here's our independent samples t-test formula on the far left there. We also compute a t-statistic, but instead of taking a sample minus a population mean in the numerator, now we're taking 2 sample means, and we're finding the difference between the 2 sample means. And in the denominator, we're going to have a standard error, but it's not standard error of the mean. In fact, it's got a long name. It's called the standard error of the difference between the 2 sample means. That's its actual name, the standard error of the difference between the 2 sample means. And here's the formula. You take the variance in the first group divided by the number in the first group, and the variance in the second group divided by the number in the second group, and then take the square root of that. So we've got my 2 sample mean differences there. The control group average cholesterol was 197.1. The nasal spray average cholesterol was 193.4. You'll see this in a bit when we do this using the programs. And the standard error is 10.85. Calculate that. You get a t with 35 degrees of freedom equals 0.34. The probability for a one-tailed test is 0.37. The probability for a two-tailed test, which we used, is 0.74. Neither of those, especially the second one, is less than 0.05, so we can't reject the null hypothesis. We can't say that those 2 sample means are significantly different. So our conclusion here would be the nasal spray does not reduce cholesterol. Even though eyeballing it, it does, right? Because 193 is less than 187. That's an observed difference. Remember, statistics, we're looking for statistically significant differences. And so statistically significant differences have to mean more than just the eyeball difference. That has to mean, what's the probability of obtaining these results, assuming the null hypothesis is true? Are they extremely rare or are they not? In this case, it's not really that rare. We're saying that that difference could be very due to chance alone, and that doesn't necessarily mean that the nasal spray reduces cholesterol. That's the whole purpose now when we do statistical tests. We're going to be calculating differences, relationship, things like that. And we want to know, is that result impressive enough? Is it rare enough? Is it uncommon enough? Assuming the null hypothesis is true, that we might think about rejecting that null hypothesis. Say like, hey, we found something so extreme here. I'm thinking that null hypothesis isn't true. So we should reject that and go with what we found. That's it.
I have a quick question
Yes.
on that. What is there a specific p-value we should be looking for to
Yes.
define that it is significant?
And you're struggling right now because I haven't showed you anything on the computer yet. But when I do all these, you will see p-values in the results printouts, and then this will all make sense. So
Excellent.
hang in
Thank
there.
you.
Yeah, just hang in there just a little bit. Okay, one more pharmaceutical company, cholesterol nasal spray thing. This one, they do a clinical trial where 13 men use the spray once per day for 6 weeks. Cholesterol levels are measured both before and after the experiment. So this is what's called a within subjects design. The one we just talked about was called a between subjects design, where you compare different people independently in different groups, and you're just comparing them to each other. This one's a better design because we've got the same guy here before and after. We're measuring his cholesterol before he takes the nasal spray and then after. Here, this guy, 292 before, 271 after, and so on. So I've got scores for 13 guys here of cholesterol levels before they started taking spray and then after 6 weeks of taking the nasal spray. This is called a dependent t-test or a paired samples t-test because these samples are not independent from each other. They are linked, they are paired. These two scores represent the same individual. These two scores represent the same individual. This is his before score, this is his after score. So that's why it's called a dependent t-test. So dependent samples t-test, we want to know if the nasal spray reduces cholesterol. We don't know if the population mean difference score before minus after, but we assume it's 0. Our null hypothesis is the most boring thing in the world. We always assume there's absolutely nothing going on. We want to assume here that the nasal spray doesn't work, right? If we're the FDA and we're thinking about giving approval, we got to see impressive results before we're going to give our stamp of approval on this. And, and also test it to make sure it doesn't, cause any really bad things, too, side effects. But we want proof that that's actually going to work. And so we go in by being ultimately skeptical and saying, let's assume it doesn't work. There's nothing going on there. We'll test it against that assumption.
I have
So
a
we
quick
collect-
question.
Yeah.
Sorry. The dependent samples t-test, is this the same thing as a dependent variable test, or is that different?
I don't know what a dependent variable test is. I haven't heard of that.
That's nursing. This is nursing statistics. We used independent and dependent, and that's what I'm trying to make it make sense in my brain, but I'll shut up.
No, it's okay. You might actually pitch me something, but I hadn't
No,
heard of
I
that term
don't.
before. So Brian, if you see something like that in print somewhere where you can email that to me,
I sure
send
will.
that to me and enlighten me, so I might be able to understand your world.
No, there's no understanding my world, but thank
Okay.
you.
All right.
I had a question too. So, when you were saying it's within subject design and that it was a dependent t-test,
Yes.
would the between subject design be an independent
Yes.
t-test?
Yes.
Okay.
Ding, ding, ding. Yes. And it's very important to understand independent and dependent samples, because independent samples, like I get 12 random people here and I throw them into the experimental group. I get 12 random people over here and I throw them into the control group. They're not connected in any way. There's no relationship whatsoever between people in this group versus this group. Those are called independent samples. But if I take one group of people and say, I'm going to conduct multiple measures on you or repeated measures on you. This is also called a repeated measures design, the dependent samples t-test, because measures are repeated on the same individual. Then I've got, dependency going on, and I can't assume independency and things like that. I don't think that's a term, independency, but we might use that for the 4th of July. Anyway, okay. So the null hypothesis for a dependent samples t-test is always the same. I don't care what values you have or anything. It's the population mean difference score between the before cholesterol level and the after cholesterol level is 0. And this null hypothesis right here, mu sub d equals 0, that's the population mean difference score. The difference score is calculated here, and we have to make sure we understand how it's calculated. We define that. We're taking before minus after. That's the difference score. And we're saying here that the average of all those different scores in the population between before taking the spray and 6 weeks after is going to be exactly 0. And our alternative hypothesis is going to be, no, it's not equal to 0. It's either going to be positive, which would mean then that the most of the before cholesterol scores are higher than the after, if it's positive, or it's going to be negative, meaning that that nasal spray actually increased cholesterol, that before they took the spray, they had lower cholesterol levels on average than after. So we can find it in either direction. We'll use an alpha 0.05, degrees of freedom, n sub d. It's not the total number of scores, it's the number of pairs of scores for a dependent t-test. So remember, I had 13 pairs of scores here. I had 13 individuals, and I measured them both before taking the spray and after. So it's not 26, even though I've got 26 scores. It's 13. It's 13 pairs of scores, or 13 different scores. That's really what it is. So 13 minus 1 is 12. That's my degrees of freedom for the dependent samples t-test. Here's the formula. T equals, and this lowercase d bar is the mean for the different scores for the sample. That's for our sample, which is 13 different before and after scores. I'm going to compute 13 different scores by subtracting before cholesterol versus after cholesterol, and I'm going to get that average or mean difference score. That goes in the numerator. In the denominator, I have a standard error of the difference scores. It's called the standard error of the difference scores. And you can see that's the variance of those different scores divided by n, and take the square root of that. And if I calculate that, I get a t of 2.58 with 12 degrees of freedom. My probability, one-tailed is 0.1, for two-tailed, which we ran, is 0.02. Because that p level is less than 0.05, I reject the null. Now, to know what conclusion I should make, how do I know, based on my p-value and things like that, whether it reduced cholesterol or not? Well, remember how I defined my difference score. My difference score was before minus after. And if I get positives overall for before minus after, that means before was greater than after. So it must have reduced cholesterol to have after scores be slightly less than before. So since that T level is a positive 2.58 as opposed to a negative 2.58, that means that the cholesterol scores were a little bit lower after they started taking the nasal spray. So my conclusion is the nasal spray reduces cholesterol. If that was a negative 2.58, my conclusion would be the nasal spray increases cholesterol. Does that mean that the after scores were greater?
So to find the mean of the different scores, would you just put both samples together into like calculator soup, or would you have to find the mean of the mean, like the mean of one?
Well, I'm not sure how we do it in calculator soup because I've never used it for dependent T before. I can show you how we do it in Vassar Stats.
Okay.
But we have to have both pairs of scores, right, side by side. And what Vassar Stats does is for every pair of scores, it computes a different score for that individual. And then for those 13 different scores, that D bar there, which is the mean of the different scores, is simply the average of all 13 different scores. That's what's in your numerator. Yeah.
So it'll give us that D bar.
I believe so.
Okay.
I don't want to lie. So, okay. I stopped sharing. Okay. Now I want to go on to show you how to do this in Vassar Stats. Are you ready for something like that? If you have sort of, glazed look right now or whatever, that can happen in statistics. So hang in there. Let me show you how to do all this stuff in Vassar Stats. And then if you have questions after tomorrow, after working on this with some of your teammates, then please send me emails, things like that, and I'll try to answer. But you can also watch this video over again too. Not that it's very good, but anyway. All right. So I want to pull up Vassar Stats.
While you're pulling that up, can I ask a quick question? Now,
Sure.
because the P was less than or smaller than 0.05, that made it clinically significant, or we could say that this actually did it in our conclusion.
That's
Is
right.
that correct?
That's
Okay.
right. Yep. If it's less than 0.05, we reject the null, which means the exact same thing as saying we have a statistically significant difference. Yep. All right. So now I want to share.
Is that less than, or is it also less than or equal to 0.05?
Oh, that's a good question. So some people when they use an alpha 0.05, it precisely means 0.05000000 or less. So if it's precisely 0.05, we still reject the null. But you'll rarely, you're going to get 4 decimal places. You're rarely going to have something that says 0.05000000. Just does not happen. But if it's 0.05 or less is the rule. Okay, so now using my small laptop, I'm going to show you how to do things on Vassar, but I'm not going to be able to see if I share my screen. I'm not going to be able to see what I'm doing. So let's try this. Why don't you guys pull up Vassar Stats on your browser, and I'll just kind of walk you through it as we're going through it and see if this makes sense. So I'm going to look at my browser now. And if you have Vassar Stats open, which is vassarstats.net, and I'm not seeing you anymore, so jump in and tell me if this gets crazy. On the far left side, we want to choose, what tests, what calculations we want to do. And there's one that's about 2/3 of the way down that says T-tests and procedures. I want you to click on that. T-tests and procedures. We're in Vassar Stats, and we're on the far left side to get T-tests and procedures. And I'm going to go back and look at my the class one more time. Is there anybody waving at me frantically saying, I have no idea what the heck you're doing? Everyone's in Vassar Stats, and everyone has clicked on T-tests and procedures. Very good. No student left behind here. All right. So once we click on T-tests and procedures, you can see that the top one is for two sample T-tests for independent or correlated samples. That's the last 2 we did. That's independent and dependent T-test. But if we're going to go back and do that one sample T-test, we've got to go down and click on single sample T-test. Single sample T-test. And it gives you a data entry thing, and it gives you the population mean. So I'm going to go back and pull up that first problem that we talked about, which was the 37 men. Yeah. And I'm going to copy and paste and do some weird stuff here. Oh, and you would have to see that to get the numbers, wouldn't you? This might not work. Maybe I just have to share now. Maybe I have to go in and share and show you what I'm doing at this point. So I'll go in and share my screen, and you can keep looking at your browser or whatever, but you can see what I'm doing here. And I want to have my Vassar Stats site. Okay, so everybody's seeing on Teams what you have open on your browser, the T-test thing. Okay, so what I've done is I've gone in my PowerPoint and I've copied all 37 of those scores. But if I paste them in there, they're going to be all screwed up. See what that looks like? So to be able to use this, I've got to go in and do hard returns after each of these scores. It doesn't have to be perfect in terms of spaces behind or anything like that, but I've got to separate all those with hard returns, which is going to take just a little while. But you know what? What better activity can you think of on a Tuesday night than to watch your instructor putting in hard returns after 37 scores so that we can see how Vassar Stats does this. Now, again, if you have a way to do this with a different program, then by all means, do that, because you might be able to copy and paste this kind of free form. And especially for one sample t-test, it might just, not have these restrictions, and you won't have to seem like, me spending all this time going through something like this. When Vassar Stats first came out like 15 years ago, it was a really cool tool, and, couldn't wait to show students the use it. Now I think it's probably rather dated. So if you're finding better things out there by searching the web that can do single sample t-test or one sample t, what we're doing right now, independent or two sample t or dependent t, find them, use them. Don't be afraid to share them with others, and you'll be popular with your teammates. But don't share them with other teams, because other teams are the enemy. And if they do well, as you know, they steal your bonus points, and you don't want that to happen. See how I've got an extra return at the bottom here? That's deadly, because it'll think I have an extra score. I don't think that 184 is going to be a problem. Remember what my population mean was in this particular problem? Mean cholesterol level for all men 55 to 65. It's been a while ago.
170.
170, very good. And you can't even see what I'm talking about. So, and then I enter that in. You got to enter the hypothetical population mean. Got to enter all your sample data up here. Hopefully it'll be okay. Hopefully I'll have 37. Click calculate. That's a good sign. I've got n of 37. And this gives me sum of squares for the entire group. The sum of x squared isn't relevant. Gives me the variance. And these are all inferential, meaning they're for samples. Sample standard deviation 32.93, standard error 5.41. Remember, that's what we had in those slides. My sample mean was 195. My population mean was 170. There's the difference. This gives me a t-value of 4.69. Degrees of freedom is 36. That's 37 minus 1. And then here, this is the magical box that I look at. If I'm doing a one-tailed test, I look at this p-value right here, and I see if that's less than 0.05. Well, it is. If I was doing two-tailed, it's also less than 0.05. So because it's less than 0.05, I conclude there is a difference. I know that my sample mean is greater than my population mean. So my conclusion is, yeah, guys who've had heart attacks have higher cholesterol than people in the general population. That's how you get that. So it's a very simple thing in Vassar Stats. Single sample T, make sure you enter all the scores right there, separated by returns. Enter in that hypothetical mean, calculate, verify all your numbers, and then reach a conclusion based on your p-values. And we'll always be using a two-tailed test on tests, by the way.
So that means the null is rejected, right?
That means the null is rejected. If that p-value is less than 0.05, we reject the null. Yep. Okay, so now, yeah, I'm going to get out of here. I'll stop sharing again. Let's go back and forth. Just try to make things confusing. I'll go back and show you the PowerPoint slide again. Let's see. Share and choose the right window. Here we go. That was my data for that first one. And just so you can see that the numbers were all the same. It's way down here. Yeah. This was the 195 minus 170 divided by 5.41. I came up with a T of 4.69, and the one tail is less than 0.05 and the two tails less than 0.05. Okay. That was the one sample T. Now here's my two sample T-test. And I've got to go enter all these numbers in now for the two sample T. So how am I going to be able to do this and see
Dr.
everything at the
Robinson?
same? Yeah.
I put all the data in the chat if you wanted to just copy and paste it, and it has all the returns
Oh,
already.
nicely done. How'd you end up doing that? How'd you get all the data and put it in the chat?
I wrote it all down as you showed us the slide, and then I was just typing really fast.
Nicely done. All right. Let me go back to, let me stop sharing this. And then let me share my Vassar. Well, see, I'm still not going to have that. In fact, why don't you guys do that? You've got all the data here for the control group in the chat. You've got all the experimental data. I'll show you how to do it in Vassar Stats. So let me go back to showing you my Vassar Stats screen. We just finished up with the single sample t-test. I'll go back to t-tests and procedures. Click on two sample t-tests for independent or correlated samples. And for this one, I'm going to be entering in all of sample A with hard returns, all of sample B with hard returns. And I want to make sure I click on independent samples up here. And then it says right below. So I'm going to actually see if I can go back and forth to Teams. And no, I can't because I'm sharing. You guys are going to have to do this. I won't be able to see the chat. I apologize. I'm on the road. I'm teaching from a hotel room, and I don't have my giant monitors where I can have everything open and copy and paste. So see if you can do that. See if you can put the two sets of sample scores that Brianna copied and pasted in the chat. Put one in sample A, that's the control group, and the experimental sample B. And when everything's in there and you don't have any empty hard returns at the end, you want to click calculate and then make sure you've got an N of 20 in A and 17 in B. And when you get that, you should come up with T values like what I have in the slides there. Has anybody been successful doing that yet? Brianna has, okay. We stop sharing and I'll go back to my slides. Brian, you have a question?
No, I was trying to say I did it. But I
Okay.
hit the wrong button.
So let me share my PowerPoint again, just going back and forth constantly here. Here's my control and experimental groups. Remember, I had 20 in the control, 17 in the experimental. I need to enter in all these scores in the appropriate boxes. And degrees of freedom of 35. And I should have ended up with a T with 35 degrees of freedom of 0.34. And you should see p-values there for one tail to 0.37 and two tail to 0.74. Is everybody seeing that when you run it yourself? Okay. It's
Yes.
very important that you're copying and pasting and putting this in the browser yourself. As you know, the thing about, observing versus doing, if you're doing it yourself, you're going to be a lot more likely to remember this on the test than if you're just trying to watch me do everything. Hope I remember it. And sometimes that doesn't work. Okay, very good. So now let's look at our last one, which is the before, after, before, after, before, after. Brandon, you didn't copy this stuff too, did you? Because I'm going to have to owe you a few $100 if you put all that in the chat. But these slides, and I'm going to have to see if I can enter those myself. So I'll stop sharing this and I'll go to Vassar Stats and see if I can start entering all that stuff in. So here's my Vassar stats. And for this one, I can use the same one. I'm going to go with correlated samples, and I've got to put in each of those pairs of scores. So I'm going to just go back and forth looking at the PowerPoint slides, and I'm going to do all the before scores first. So here's how that's going to work. I know this is a little embarrassing, but my short-term memory is really short. So
Brianna was actually able to copy and paste them. So she has them in the chat.
you have them in the chat?
They're in the chat.
Then why in the world would I be doing any of this? Let's see if you guys can enter all this in sample A and sample B. It's very important that you make sure you have the before and after sample A, sample B lined up so that it represents the same person. You should have no more than 13 scores in each, and then click calculate after you have 13 and 13. Remember, these have to be lined up perfectly because that very first person is person number 1. And then when you calculate, you should see at the bottom, and I'm looking at my results for this, you should come up with a T with 12 degrees of freedom of 2.58 and very small p-values. Maybe I'm a little fast for you here. Wait for you to catch up. Has anybody entered all 26 and got those
Yes.
values?
Yep.
Good. Okay. Okay, then what you've done then is you've done everything you need to know how to do for Thursday, because there will be